Hi, this is Barrett Givens, and in this video, we're going to talk about the definition of being continuous at a point. And we're going to compare the definition that a topology student would consider versus the definition that a real analysis student would consider. Okay, so we're going to assume that we have a function f that goes from R to R, and assume that R has the standard topology in both cases. So the topology with basic open sets being open intervals. The real analysis student says, well, f is continuous at a point x equals a, if and only if, for all epsilon greater than 0, there exists a delta greater than 0, such that for all x, if x minus a in absolute values is less than delta, then the absolute value of f of x minus f of a is less than epsilon. That is what's known as the epsilon delta definition of continuity. It's very well known, beloved by all students, I'm sure, or at least it's well known, okay? Now, a topology student might go to her friend and say, that's not the definition we use in topology class. In topology class, we say f is continuous at x equals a. Well, first of all, f is continuous if the pre-image of any open set is open. So if U is an open set, then f inverse of U has to also be an open set. And to be continuous at a point means you have to have an open set around that point. Okay, so if U is an open neighborhood of f of a, then f inverse of U is an open neighborhood of a. So being continuous at a point A means we look at open sets that contain the relevant points. So now let's say you, a topology student, want to convince your friend, a real analysis student, that that the topology definition really does imply the real analysis definition. In fact, the two definitions are equivalent in this situation where you have a function from R to R. But I'm just going to show the proof just for one direction, that the topology definition implies the real analysis definition. And what I'm going to do is I'm just going to reveal the entire proof, but then we're going to read through it line by line really carefully. Okay, here's a proof. You might want to stop the video right now and just read through the proof. And then once you've read through it and kind of thought about any places you might have questions, then go ahead and watch the rest of the video where hopefully I answer all your questions as we go. Okay, so we are going to assume the topological definition of continuity. So suppose that f is continuous following this topological definition. We want to prove that f is continuous following the real analysis definition. So we have to do a real analysis style proof of continuity. So in the real analysis style proofs of continuity, we always start by saying, okay, the definition says for all epsilon greater than 0. So we always start by saying let epsilon be greater than 0. And then the next step is we want to say then there exists a delta. And so what you want to do is, in a real analysis proof, you might sort of do some scratch paper work, and then you might say something like, let delta be less than epsilon over 3 or something, okay? But here, what we're going to do is we're going to apply the topological definition. We're going to do a bunch of topology, and then a little bit further down, we're going to find out what our delta is, okay? So what I'm going to do is I'm going to start with a U. I'm going to let U be f of a minus epsilon, f of a plus epsilon. And somehow I have an extra parentheses here, so let me just fix that. Okay. So U is an open neighborhood of f of a. So U is this open interval that contains f of a. There's my set U. And then if I look at the topological definition, so the topological definition says if U is an open neighborhood of f of a, then if I assume f is continuous by this definition, then f inverse of U is open. And furthermore, it contains A. Okay? So let's look at what f inverse of U is in this example. Okay, f inverse of U is I look at the set U on my vertical axis, and I look at the portions of the graph that kind of correspond to being inside of there. And then I pull them down to the x-axis. So I pull them down to the x-axis. My vertical lines are not always as vertical as they might, as one might hope. Okay? And so the inverse image of U in this particular example consists of these three open intervals. So this is my f inverse of u in this example. And if I assume that f is continuous by the topological definition, then f inverse of u is open. F inverse of u is open. And it contains A, so it's an open neighborhood of A. The definition of being an open neighborhood is that there exists a basic open set, C comma D. So my C comma D would be just this part of the intervals. That's my CD. CD. So I've got A inside this one interval, C comma D, which is a subset of all of F inverse of U, because in this example, F inverse of U has like multiple chunks to it, okay? Now I'm going to zoom in a little bit here. Unfortunately, I sort of drew it so that A does look like it's right in between C and D, but maybe A is a little bit to the left on this one. So what I will do is I will choose my delta. I'll choose my delta so that A minus delta, A plus delta is inside of C comma D. So in this example, maybe A is a little bit closer to C. And so delta will be the distance from A to C and A to D. It'll be the smaller of those two distances. Okay, so I'm going to choose my delta down here to be the distance from A to D and from A to C, and I'll take the smaller of those two. And so that means that the interval A minus delta, A plus delta is a subset of CD. All right, let's go back up to the definition of how the real analysis students thinks about epsilon delta proofs. We start with for all epsilon greater than 0. And then we say there exists a delta, so we have to say what the delta is. Well, I've done that now. I've let delta equal this quantity. Okay? And then I've shown that the point A is inside of the interval A minus delta, A plus delta. That interval is small enough that it's inside of this other small interval, C comma D. And this interval C comma D was chosen to be one of the intervals that makes up F inverse of U. And so I've got A in this interval, which is contained in this other interval, which is contained in F inverse of U. And I see all of that on my picture over here. Okay, now going to the next step of the definition of real analysis and continuity. I started with epsilon greater than 0. I did a bunch of stuff. I eventually got my delta. I found my delta. Now the next part of the definition says for all x, if x minus a is less than delta. So I'm going to assume that x is given and x minus a is less than delta. If x minus a in absolute values is less than delta, that means the distance from x to a is less than delta. So that means that x is in this interval a minus delta, a plus delta. But this interval a minus delta, a plus delta is a subset of f inverse of u, so x has to be an element of f inverse of u. But the meaning of being in f inverse of u, the definition of x being an element of f inverse of u is that f of x is in u. And remember now what u equals. U equals f of a minus epsilon, f of a plus epsilon. So f of x is inside this interval on the vertical axis, close to f of a. It's within epsilon units, plus or minus, of f of a. And so that means that f of x minus f of a is less than epsilon. And that's the final step in the epsilon delta definition. F of x minus f of a is less than epsilon. And that's what I got here. So we can see that I proved using the epsilon delta definition that if a function is continuous using the topology definition, that if I start with some epsilon greater than 0, I can use the topology definition to eventually get a delta. And then I can find out that if that a is inside of this interval, a minus delta, a plus delta, which is a subset of f inverse of u. Then I let x be arbitrary, and I assume that x minus a is less than delta. And then I do a bunch of stuff with the sets that I found, and I get f of x minus f of a is less than epsilon. And so that means that I've shown, using the real analysis definition, that this function is continuous. So what I've shown now is that if a function is continuous using the topology definition, a function from the reals to the reals, then it is also continuous using the real analysis definition. Okay? And it is in fact true that it goes the other way. A real analysis student should be able to convince a topology student that the real analysis definition also proves the topology definition if the function's going from the reals to the reals. Okay, thank you for listening.